In this video, I want to look at transformations in the complex plane. Before we do that, I want to look at transformations in just one dimension, along the x-axis. Let's think of a translation of 2 units along the x-axis. 1 would go to 3, 2 would go to 4, minus 2 would go to 0. I could draw lots of arrows, a sort of arrow from 1 to 3, an arrow from 2 to 4. That would be quite a big mess. What we usually do is to draw a y-axis, and then we think of our translation as the function y equals x plus 2. And here we have the graph that you're familiar with. And thinking of it in the way that I was thinking just now, we can think that 1 is mapped onto 3, 2 is mapped onto 4, and so we have a way of representing our translation of 2 units along the x-axis, y equals x plus 2, with a straight line graph. What happens when we think in terms of complex numbers? Let's now think of a translation of 2 minus I in the complex plane. We can't really see that very easily as a translation of the whole plane. It would be even more of a mess than we had before. And we can't really put a y-axis in. I'm starting with 2 dimensions. My domain has 2 dimensions. My range has 2 dimensions. So if I was going to have a sort of xy diagram like I had before, then I would need 4 dimensions. An interesting idea. Instead of trying to do anything that complicated, we draw 2 diagrams. One, a complex number plane representing the domain. We call this the z-plane, and we have z is x plus iy. And the second diagram, the range, which we call the w-plane, and in this case we have w equals u plus iv. We're now in a position to look and see what happens if we start with the circle mod z equals 3 in the z-plane, and we translate it through 2 minus I. So here's mod z equals 3 in the z-plane, a circle, center of the origin, radius 3. If I translate that 2 minus I, the center becomes 2 minus I. That's all that's happening, so it still has a radius of 3. So we have a circle in the w-plane with center 2 minus 1 and radius 3. Its equation is quite simply mod w minus 2 minus I equals 3. I want to look at this algebraically. It's a very simple example, but the process that we're going to look at will work when we have something much more complicated. We're starting in the z-plane and we're translating through 2 minus I. So if I start with z and I translate through 2 minus I, then I have z plus 2 minus I. That's where z has gone if I've translated through 2 minus I. So this is w. And we're starting with mod z equals 3. Well, taking the equation here, this tells me that w minus 2 minus I is equal to z. So if we start with mod z equals 3, then mod z equals 3 means that mod w minus 2 minus I equals 3. And that is the equation of the circle that we had in the w-plane at the top of the page. So that we got by common sense. This we did by algebra. As I say, it's a very simple one, but the same technique is going to work for us with something more complicated. Now let's look at an enlargement, factor 3, and center the origin. This time I've started with the circle mod z equals 2 in the z-plane. If we enlarge that factor 3, it will become a circle of radius 6. So we know the answer. In the w-plane, we have a circle, center of the origin, radius 6. Its equation must be mod w equals 6. I'm going to do the same thing with the algebra as I did just now. We're going to start with the equation mod z is 2. If we enlarge factor 3, center of the origin, then z becomes 3 times z. Wherever z is, it's just 3 times the vector. So this is w. This now we rearrange to get z. We know that mod z is equal to 2 to give us the circle in the z-plane, and therefore the image in the w-plane comes from putting w over 3 instead of z, multiply both sides by 3, and we get mod w equals 6, which was the equation that we got from common sense. Mod w is 6. So a couple of easy examples. The technique at the bottom, this algebraic technique, is one that we're going to use when we have things which are not so easy to see.